Okay, welcome back. As we take a closer look at the light-dependent reactions of photosynthesis, first I want to kind of give you a roadmap. So here's the overall photosynthesis. We've seen this picture when we did the overview notes. We're going to focus now on the light reactions, the light-dependent reactions. This is the photo part of photosynthesis. This is the synthesis part where you're making the sugar. So we need light, we need water, we produce oxygen, we produce a little bit of ATP and some NADPH. So let's get started. In the light-dependent reactions, first you want to be aware that they happen in the thylakoid membrane. Remember that the thylakoid were sort of like those little coins, but it occurs in the membrane of the thylakoid. Okay? We have two photosystems that we're going to look at. Photosystem 2 and Photosystem 1. They're named after their origin of discovery. So Photosystem 1 was discovered first and then Photosystem 2. But when we look at the process, I'll pull this picture up. When we look at the process, Photosystem 2 actually we'll talk about first and then Photosystem 1. All right, so we know we need light, and light is going to come in as photons. So we get two photons of light coming in, and they would be absorbed by our pigments. In this case, we're going to specifically talk about chlorophyll. And the area where they come in is called the light harvesting complex. The light harvesting complex is basically like an antenna. Or like a satellite dish. So if you think about this, when the light comes in, right, the energy bounces around from pigment to pigment to pigment, but it's all being funneled in to one location, okay, right here. So just like a satellite dish funnels in the waves into one location, the light harvesting complex does the same kind of a thing. When that happens, it excites two electrons in the reaction center. So that's right here, okay, in the reaction center. And that's kind of like the receiver. So again, that's the reaction center is where all of that energy is being focused. And so much energy is absorbed by those electrons that they actually move from the atom. So those two electrons get boosted to the electron transport system or electron transport chain of that photosystem. Remember previously we talked about a photosystem has three things: a light harvesting complex, an electron transport chain, and then it has pigments to be able to absorb that light. Now, just like cellular respiration, the movement of those electrons is going to release energy. And that energy is used to pump hydrogen ions, but this time you're pumping them into the thylakoid space. And on the previous picture, that was called the lumen, the inside of the thylakoid, right? So here's your thylakoid, here's the space inside. You're building up this hydrogen ion gradient inside of the thylakoid. And just like cellular respiration, that gradient is going to be your proton motive force, right? Your proton motive force. And that means that you're going to have energy available to power chemiosmosis. Do you remember what that means? Basically, you're making ATP. So yes, even in photosynthesis, go back to this picture, making a little bit of ATP here, but it's not for the cell to use, it's for the Calvin cycle to use. It's for the other half of photosynthesis to use. So what we just talked about, if I actually go back to this picture here, is light comes in to photosystem 2, energy moves around, focus that energy into the receiver, right? And so water is going to donate electrons to this location. When water is split, oxygen is released, right? We talked about the origin of oxygen is not from CO2, origin of oxygen actually comes from water. So those electrons receive energy and then they're boosted to the electron transport chain. We'll focus a little bit more detail about that in a few minutes. So photosystem 2. Now it says while reactions occur in photosystem 1 is also occurring. So these are happening simultaneously, okay? But the same process, same basic process. 2 photons of light are absorbed by chlorophyll in that, I'm going to abbreviate this, light harvesting complex, right? This still excites 2 electrons in the reaction center, and those electrons are boosted to another electron transport chain of photosystem 1. Switch back to my picture. It's like we said, light comes in, energy is moved, electrons are excited. Here's the electron transport chain of photosystem 1. Okay. But it says photosystem 1 immediately obtains replacements for the lost electrons from the last electron carrier in photosystem 2. So let's look back at the picture. When these electrons move, they are falling or moving to photosystem 1. So when photosystem 1 loses the electrons, the new electrons come in. So it's immediately replaced. Okay, this prevents electrons from falling back down. Same thing over here. When these electrons are boosted, the electrons from water come in, and that prevents them from falling back down. So it's keeping electrons flowing in one direction. Keep them going forward. Keep them going forward. Okay. Electrons passed in the electron transport system of photosystem 1 actually go to NADP, NADP plus to make NADPH. So here is our electron carrier. This guy, NADP plus, does not have electrons. NADPH does. So just like NAD plus in cellular respiration, think of the P in here for photosynthesis. This molecule is used during photosynthesis. Now these electron carriers are going to be used, switch back here, NADPH from the light reactions is going to take electrons to the Calvin cycle. So NADPH leaves the thylakoid and goes out into the stroma, the space out here. Okay. Like I said before, when that water molecule splits, it maintains electron flow in one direction. Because electrons move in one direction, we want to replenish the electrons in photosystems to reaction center by splitting that water molecule. Like I said, going back to this picture, here comes the water, split it, electrons are donated here. So when they get boosted, they can't fall back because these electrons come in and take their spot. So there's only one direction for them to go. So here's the kind of equation for this. When you split water, you get 1/2 of that diatomic oxygen, 2 protons, and 2 electrons. The oxygen that is released can be used directly by the plant for respiration or given off to the atmosphere. There is going to be more of a net production of oxygen than what would be used during cellular respiration. All right, I'm going to stop there with these notes because the rest of this goes on to the light-independent reactions, which we will tackle again. So watch the video link on Schoology for more information.